Hi, hello. This is the topic 10, cell communication. And from this topic, from now on, we have six topics, just focusing on the nervous system. And this is the first topic. And then you may see it a little bit different. Then the case is my drawing pad broken. My drawing pad is broken, so I cannot draw anything. And so instead, I will just go through the slides rather than draw on the drawing pad. Yeah, and I don't think I need to show my face anymore. So, yeah, so let's continue through the slices, and the uh, the first let's continue. The first thing let's consider is that whether the thing about all of those multiple cellular organisms. And I mentioned before, any multiple cellular organism, not merely that all the cells join together, but they have to communicate with each other. For example, what if I just touch something super hot, and it damaged me, and I retrieve my hand. So in that case, the sensing cells is totally different than the cells that are used to retrieve my hand. So how these two cells communicate with each other, that's a essential problem or issue any multiple cellular organism must solve by themselves. And what kind of cells have or what kind of multiple cellular organisms? We have mushroom, fungi, or mushroom is a type of fungi, plants, and animals. And all of those different kingdoms has their own way of communicate with each other. In total, a common way is that one cell produces some chemicals, and this chemical was released to the nearby space of this cell. And then these chemicals can be sensed by another cells closely next to this cells, and this we call it paracrine. Paracrine is the most common way that two cells, or one to multiple cells, can communicate with each other. Even in human being, we do have a lot of paracrine happening in our body. And in some animals, including not only in some animals, and not only animals, plants, and some big fungi, they do have a vascular system or circulatory system. And in this case, this messenger chemicals can get into the vasculature and can be delivered into a long distance. And in this way, the these chemicals can be not only have an effect in a long distance, but also have a systemic effect. Not the cells close to the original cells, but also any single cell that have been touched by the circulatory system can be affected by this chemicals, and this we call it the endocrine system. So endocrine system can cover a long distance, but it's not specific. It's systemic. Every other cells has sense it. Another is very specific is that these two cells can contact each other just by the proteins that are attached to each other on their membranes. And this is super specific. However, this is also very short distance. You can see the two cells must contact with each other. So then that's the overall introduction of the cell-to-cell communication. And then next we just talk about one specific system, that this system can mediate the long-distance communication, and also very specific from cell to cell. And this is the nervous system. The nervous system is something specific to animals, and actually it is the feature of animals. All animals have a nervous system, and no other creatures or organisms have this nervous system. And what's special about the nervous system? The number one thing is the nervous cells. I'll call it a neuron. A neuron has a cell body around here. This is a cell body and a long and multiple tentacles. There's one super long we call axon, and multiple small one we call dendrites. And then, so how a nervous system can deliver the message from one places to another places over a long distance and very special, and also to release the signal to a specific cell. is actually by the long axons. And then these long axons form we call it synapse, attach or patch to the target cells. And so in this topic, we're going to talk about how the signals can be transmitted across the long axons. So the long axons look like a wire, but the signal transmission is totally different than how the electricity can be transmitted through a metal wire. Next, we talk about how it happens. Before we even talk about how this signal is transmitted, let's first introduce a concept called a membrane potential or resting potential. The resting potential is that, so here's the cell membrane. Across the cell membrane, all our cells carry some electrical charge. Any cells in our body have electric charge, and some of those cells carrying a higher electric charge. Some of those carry a lower electric charge, and this electric charge is called a resting potential. And all the resting potential are negative. All our cells carry a negative electric charge. Why I carry this one? That's because a protein called a sodium potassium pump located on the cell membrane, and this pump keep pumping 3 sodium out and 2 potassium in. So it is imbalanced. It pump out more cations out than it pump cations in. As a consequence, the cell carry a negative charge. And then, this is an imbalance. Once this imbalance, the resting potential is broken, this neuron or this cell is activated. So the first step, how to activate this one? That's the first. Only in this class we call it first step ion channels. And from now on, you listen, you'll hear a lot of opening, inactivation, and closing of different ion channels. And this is a series of ion channel activation and inactivation. That is what happened. That is what happened when the neuron is activated. And so the first step ion channels, again, first step ion channel is the word I invented. Only is only used in this class. If you talk about someone else, like first step ion channels, they don't know at all what it means. So first step ion channels is that these ion channels can be activated by special stimuli. Here I give you 2 examples. For example, this channel called piezo 1, piezo 2. If you remember, we talked about the Merkel cells under the skin. Merkel cells carrying the ion channel called piezo 2. What's their function? Whenever we push on the cell, when there is a pressure push on the membrane, this pressure open up the piezo 1 or piezo 2. So this is a mechanical pressure sensor. Another sensor called TRPV. TRP is a large family of sensor, and the TRPVs are those sensors that can be opened by temperature. When the temperature get into a certain range, this TRP 1, 2, or 3, or 4, they open up. So those are the sensors that those are the channels that can be opened by a certain condition. And then this is at the very beginning. This is how our body sensing the stimulus, and because all of the stimulus have some way to open up the ion channels. When this ion channel is open, this is the first step. This is the first step that to activate this neuron. And once this neuron is activated, it sends a signal to other neurons and give us a sense. And both piezo and the TRPV are we call the ion channels that are responsible or sensitive to external stimulus. But in our body, there's so many neurons in our body. Most of those are intermediate neurons, which means these neurons are not directly activated by external stimuli, or sometimes actually internal stimuli. But anyway, they are not directly activated by stimuli, but rather they are activated by another neuron. So how another neuron can activate a next neuron? Actually, this is something we will talk more in next class through the synapse. But in here, we only talk about after. So basically, the previous neuron release some chemicals and received by the next neuron. And in this topic, we just focus on what kind of molecules, and these molecules has to be ion channel. What kind of ion channels? The sensing the messenger that deliver the release from the previous neuron to the next neuron. And there's two type of the channels. One type called ligand gated ion channel, which means once a ligand means any small molecules that can bind to a protein to activate this protein, we call it ligand. And ligand gated means if this ion channel can be opened by the small molecule, they call it ligand gated ion channel. And in contrast, another type of a channel, this is called a G protein gated ion channel. What does it mean? It means that this type of ion channel does not have a ligand capturing domain at all. However, this messenger bind to another protein, this protein called a G protein. Once this G protein bind to the ligand, and then a subunit will be released from the G protein. And then this subunit is floating in the cell membrane. And then this floating subunit will next bind to the ion channels, then to open the ion channel. So this is called G protein gated ion channels. And to compare the ligand gated and the G protein gated ion channels, the ligand gated ion channels has a quick response, but the response is not as strong as a G protein. G protein gated normally has a delay because it has to activate the G protein first. But once G protein is activated, one G protein can activate multiple ion channels, so G protein can amplify the signal, normally trigger a very strong response. And then, however, next, let's see. The activation of the first step ion channel doesn't mean this neuron is definitely being activated. And it may be activated or not be. But one thing for sure is that the first step ion channel will never completely reverse the resting potential. Only when the resting potential is completely reversed, this neuron will be activated. It cannot reverse the neuron reverse resting potential at all. Rather, actually, there's a second step ion channel that will be opened in response to the first step ion channel. This is called a voltage gated ion channel. Voltage gated means this ion channel is gated by the voltage. When the voltage increased, this voltage gated ion channel will open. In the case of neurons, there's only one type of voltage gated ion channel that's responsible for the activation of this neuron. They call it voltage gated sodium neuron. Voltage gated sodium neuron is open once the membrane potential is elevated to a certain level. On this level, called it threshold memory potential or threshold potential. So basically, one is external internal stimulus coming to this neuron and is activated. It's open up the ion channels, first step ion channels, and then when the first step ion channels when it open, cations, in many cases it's sodium, in some cases also calcium, get into the cells. When the cations, the positive ions get into the cells, the membrane potential increase a little bit. In some cases, it doesn't increase all the way to the threshold, then nothing happens. Even though there's some stimulus, this neuron is not activated. We don't sense anything. But if the signal is strong enough to elevate it, the threshold all the way up above the threshold, and then massive voltage gated sodium channel will open. And then when the massive sodium ion channel open, a lot of the sodium get inward to the cells. Keep in mind, resting potential pumping out sodium, so there's always more sodium outside cells in the resting potential and lower sodium concentration inside the cells. So in this case, when the voltage gated sodium channel open, massive sodium get in, and then this membrane potential gradually, rapidly going up and all the way up, and then but it reached some level. This level called a peak potential, and when it reached the peak potential, it stopped there, and it's not unlimited going up because this sodium voltage gated sodium channel will inactivate by itself. Will be inactivated by itself. Call it inactivation, free inactivation segments. The segments. So basically, again, this sodium channel only open transiently or temporarily. Very shortly, this N channel will be closed again by this inactivation segments. And this closing, we do not call it closing. This is called inactivation. Please keep in mind, this is very important. Inactivation and the close. The ion channels have mainly 3 steps: open, close, inactivation. What's the difference between inactivation and close? So open means is open. Ions can come in. But what is different between close and inactivation? Close, before this neuron is activated at all, this ion channel is closed. And when it's closed, it means it's ready. It can be activated anytime as long as you increase the voltage or you have the stimulus. But what's mean by inactivation? Inactivation will gradually return to the closed status. But when this ion channel is under the inactivation status, it cannot be open at all, no matter what kind of stimulus you give it to it. Okay, so that's the difference between inactivation and the closed. So once it's going all the way up to the this is what I mentioned. This slide is so when it go all the way up to the peak potential, this sodium ion voltage gated sodium ion closed, and this kind of closed, open, inactivation and closed. This pattern apply not only to the voltage gated sodium channel, but also to many other like a piezo, TRPV. Most of those ion channels follow this pattern. First, when it's closed, it's ready to be open, and when it's open, it soon be inactivated, and then it's from inactivation to close gradually turn to closed status. And when it can turn to a closed status, can be open again. And this is very important because it protect us from being constantly sensing the persistent or repetitive stimulus both outside the body and inside the body. And then and one is member potential reach the peak value. Now you know the sodium ion channel closed. Another thing happened is that another channel called a voltage gated potassium channel opened. And this, again, please keep in mind, when the cells is under resting potential status, the potassium ions is higher inside the cells, and sodium ion is lower inside the cells. So sodium higher outside cells, potassium is higher inside the cells. So when this channel open, driven by concentration gradients and also the electricity, now the cells carry a positive charge. In both ways, potassium should go out. And this channel, we call it an outward channel. And there's another thing we just mentioned here that we haven't mentioned before, but is applied to previous channels. Some channels are only one direction. For example, the voltage gated sodium channel we just mentioned is an inward, means it only allows the sodium to get in, not allow the sodium to get out. And this voltage gated potassium channel is outward, which means only allowed potassium channel getting out but not in. But for the piezo, but TRPV, both of those are bidirectional. So this is not universal, but some of those are inward, some of those are outward, and some of those are bidirectional. And also, by the way, the voltage gated sodium channel and potassium channel are quite identical in all neurons, almost identical in all neurons. They are basically whenever you finish, whenever the cells is activated, is always these two channels taking care of the rest of the rest of those works. And then again, so what happened when voltage gated potassium channel open? The potassium get into the cells, and then when the potassium get into the cells, potassium will get out of the cells. Potassium ions will get out of the cells. When the potassium ion get out of the cells, you can imagine the cell's membrane potential dropped dramatically. And this, it kind of return to the status of the membrane potential. This is called repolarization. And then in some cases even go further down, even lower than the original resting potential, and this is called a hyperpolarization. And and then when the cells go into the hyperpolarization, from this hyperpolarization also has the voltage number is similar as the resting potential, but actually totally different than the resting potential, resting status. Because in the resting status, again, you have higher potassium inside the cells and higher sodium outside the cells. But during the stage of early hyperpolarization, you have the opposite way. You have a higher potassium outside the cells and higher sodium inside the cells. So in these cases, if some stimulus coming to the neuron try to activate this neuron is very, very hard to have a response to any of those stimulus because the sodium and potassium gradient has not been restored yet. What kind of a protein restore this gradients? Potassium and calcium pump again. So during the hyperpolarization period, this pump gradually pumping 3 sodium out and 2 potassium in to restore the resting status. Before the resting status is restored, you need an extremely strong stimulus to activate this neuron. And that is after that the cells return to the return like this status, return as at least the member return to the resting potential. This is called, and this area called a relative refractory period. And this time the neuron may be activated, but you really need a strong stimulus. But from first reaching the threshold till the repolarization to the resting potential number, this period called absolute refractory period, because at this period, no matter how strong the stimulus is, this neuron cannot be activated at all. Why is that? Because if you remember, those voltage-gated sodium channels, those voltage-gated potassium channels, all are inactivated. When they return to the closed status after the repolarization return the number to the membrane potential. So during the hyperpolarization, this voltage-gated sodium channel and the voltage-gated potassium channel return to the closed status. And that's why if you have a really strong stimulus, you can activate the neuron in some way. But before this, one is inactivated, from the depolarization period to the repolarization period, both voltage-gated sodium channel or voltage-gated potassium channel are inactivated. They cannot open at all, no matter how strong the stimulus is. So this is called absolute refractory period. Overall, during the refractory period, it's extremely hard or impossible to activate the neuron at all. And this is important to make sure that the neuron signal transmission is only one direction. Now let's talk about this is summary pages. Okay, now let's talk about how this neuron signal is transmitted. How the neuron signal is transmitted. We just mentioned that like one local space, it can be activated, but it's only one local place. And if you want to transmit it, you have to send a signal all along the axon. How does it migrate all along the axon? That's because just imagine that this one place has action potential. Sodium get in. And can sodium just stay here? No, sodium will not just stay here. Inside the cells, this a water-based solution. By diffusion, sodium will migrate to both direction of the original activation area. And honestly, I don't know what happened on this way. it may generate another action potential this way, but it is focused on this direction of the axons. All axons has only one direction of nerve signal transmission. So when the sodium migrate to the next place, what happened here? More cation, more positive ion migrate here. It basically increased the local memory potential. And what happens if the local memory potential be elevated? The voltage gated sodium ion channel will open. And what happens if the voltage gated sodium ion channel open? You have action potential. So, oh yes, I forgot this one. So overall, this series of this open the change of the memory potential and the opening and closing all of the ion channels, this we call action potential. Whenever an action potential happens, it means this neuron at this area is activated. And then they're coming back here. So when this sodium migrates to the next places, it triggers the action potential in the next places. So then in the next places, you don't really need a stimulus. You just need your neighbor have extra potential. And then now this has extra potential. It has sodium get into the cells. And this sodium also diffuse further forward. And then it trigger the extra potential of the next places. So basically it's like extra potential happening in one places, another places, another places. Sequentially happening of extra potential. This we call it the propagation of action potential. The propagation of action potential is how the neural signal is transmitted along the axon. And again, this is only one way. Why this is only one way? Because think about here. In these places, you have an action potential happen. The sodium ion trigger an action potential in next places, but it cannot trigger another action potential in the previous place because this place just happened to have an action potential. Now is under a refractory period. It cannot be triggered. It cannot be activated at all. And this figure is the original one is stimulated by a needle, by an electric probe. That's why I don't know whether it's directly in this place, in these places, there also should be action potential to be activated theoretically. But in the real world, in the real body, it never happened that an axon can be activated in the middle. They're always from the root of the axon. So in these cases, the nerve signal is always transmitted in one way. And how fast they can be transported? If only through the potential propagation, it's actually pretty slow. It's about 1 meter per second. It's rather slow. And in human, that's the speed in human, because our axon is rather small. In some other animals, like a giant squid, their axon can be as large as visible to the eye, 1 millimeter. In their case, their transmission rate is much faster, 25 meters per second. And but of course, we're smarter than the squid, right? And our nerve signal transmission is much faster than the giant squid. How? Because we have another way of making them faster. This way is called the myelination. What happened in our body? Many of those axons does not exist in a naked way. Rather, they are wrapped by another special cells. We talk about these cells later, Schwann cells or oligodendrocytes. We talk about in the next class. And in this class, we just call this a myelin sheath, or a myelin segment. This a myelin sheath segments. So in these places, this myelin sheath is highly rich in lipids. Lipids is not a good conductor or no conductor. Lipid do not conduct electricity, right? And then when it's tightly wrapped, this segment, this region, tightly wrapped in a myelin sheath, which means there's no sodium at all outside the cells. And think about this. Here, this region, you have some action potential happening right here. And then you have a lot of sodium ion getting into the cells. And the sodium ion migrate to the next region. If it's naked, it will trigger another action potential right here. However, this is protected by the myelin sheath. Even though there is voltage gated sodium ion channel here, even though it can open, there's no sodium ions outside. Nothing will get in. So here, no action potential will be triggered at all. In this case, the sodium will not be disturbed. The sodium diffusion will not be disturbed at all. And sodium will keep diffusing further. And another thing, please keep in mind, sodium diffusion rate is much faster than the propagation of the action potential. So it takes shorter times for the sodium ions to migrate from this place to the next place, and then these two places does not have any myelin sheath, called the node of Ranvier, and this place is naked, and action potential can happen in these places. So basically, the sodium ion diffuse a long distance to the next node and activate the action potential in the next node, and then the next node and the next node. In these cases, if you say action potential propagation in a naked nerve is a walking along the nerve, and this a leaping or jumping on the nerve. And this is only an illustration. The real thing is like this. You see the three green dots are the node Ranvier that really go past or cross a long distance from here to here to here. So in this case, the nervous signal transmission will be much faster in the myelinated nerves axons than naked axons. What's the difference? Here has a different. These axons are also called the nerve fibers, and in our body we have a different type of nerve fibers. The fastest one, they call it alpha or gamma or alpha or 1A or 1B. All of those are actually pretty. If you look into their structure, pretty similar. The thickest one. The axon itself is thick, and the myelination is also thick. And then there's a long myelination. So this can go the fastest. How fast it can go? About 100 meters per mile, or 270 mile per hour. Actually, it's much faster than I drive. That's very fast. And the alpha, we call it motor fibers. Those are the fibers coming out from our brain or the spinal cord, go to the muscle to control the contraction of the skeletal muscles. And those are the fast one. And then for the 1A or 1B are also the thickest and the fastest. They are sensing a special sense. We call it proprioception. What do you mean by proprioception? If you listen to this video, you try to close your eyes. If you close your eyes, do you know where's your hands? Where's your hands is? Where's your feet is? In most cases, no matter we open or close our eyes, we always know where our body is. You always know you are sitting or standing. That's the sense of a proprioception, the sensing of our body position. How we sense it? That's based on. It's a calculation. We don't have to do the calculation by ourselves. It's a calculation based on the length of each muscle we have. So basically, this is a sense of the length of each muscle. And then by sensing the length of each muscle, we know where exactly where we are, or not where we are. We know exactly what's the position we are. And this calculation happening in the brain, it doesn't need the interference our own consciousness. And then it is many different fibers, but in this class, the only thing it requires is not the only thing, but the most important thing is which one is the fastest one. The thickest and the fastest is both the skeletal muscle and the proprioception. And also there are two types of nerves: motor fibers deliver the signals outside the brain and the spinal cord. They call it central nervous system, which we'll learn in the next topics. And then the sensory fibers collect the sensing signals back to the brain and the spinal cord. And all our nerves in our body, like the blood vessel, are one directional. Never have a bidirectional thing. It's going out, it's going out, always going out. It's going in, always coming in. And that's it for today's class. And have a good weekend. Bye-bye.